Hi, and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking a little bit about center of mass motion. So this is a continuation of our present discussion about linear momentum and its conservation. So in order to kind of facilitate that, we'll start with a little bit of where we've been so far, and then I'm going to show a little bit of a simulation and then maybe discuss it a little bit. So let's begin by recalling sort of the territory over which we've treaded. First of all, we have our definition for linear momentum. We use P to represent linear momentum. It is defined for an object as the mass of the object times the object's velocity, at least classically. So we'll put P is linear momentum. And then the other thing that I have previously defined that is sort of relevant here is center of mass. So center of mass, we usually use something like an XCM or an SCM if you wanted it in 3 dimensions, but in 1 dimension, X center of mass is given by basically taking each element that makes up an object and taking the mass of those elements and multiplying by the position of those elements, adding them all together, and then dividing by the total mass. So this is the shorthand way of writing that as an equation. So this is center of mass position. And this is kind of in 1 dimension, but you could in principle do this for X, for Y, and for Z, and then you've got it in 3 dimensions Cartesian. Third thing to recall is that Newton's force laws basically imply linear momentum conservation within a system. Alright, so with these 3 basic principles in position, and by the way, this last one, if you want an equation, we would say like the sum of all of the initial positions, we're summing on index j, I here is for initial. If you were to sum for all of the linear momentums initially and finally, you should get the same sum. So with these things in mind, let's hop over to a simulation and look at it. Look at kind of like a simulated demo of that. So we're going to use the Colorado PhET website. This is a website where I build a lot, or use the simulations for a lot of my virtual labs for online courses. And we're going to pick this simulation right here. It says Collision Lab on it. And we actually should be able to just open it up and play. Now I'm going to resize my window just to make it a little easier to see what's going on. There are, of course, a variety of possible collisions that we can look at. For our purposes, the Intro 1 and the Explore 1D are the relevant simulations that we want. I have here basically 2 masses labeled 1 and 2. They have some initial velocities, and I can actually put a center of mass. So that happens to be right here. And you'll notice if I sort of look at the more data option here, and if I look at the relevant masses of the 2, I can change things like where is the center of mass between the 2 of them and so on. So here's the mass of 1, here's the mass of 2. This one's actually 3 times bigger than that one. But if we change it so that they are the same mass, so 0.5, and to enter, I don't know if it'll let me enter with my little face over the top of it. Enter. This may mean that I'm going to have to move myself around in this diagram in order to do this simulation, but they're now the same size, and you'll notice that the center of mass is now midway between them. And if I change this thing to have a value of 1 instead of 1.5, then the center of mass moves a little bit closer to the bigger object. And you can actually just play around with the two masses and their positions. There's like a little built-in meter stick up here, and you can, in some sense, verify that this equation is working out. For two objects, the center of mass equation would look like this. We basically use the mass of the first times the position of the first plus the mass of the second times the position of the second divided by the total mass. So in the example of this system that we have here, where I have 1 and 2 and they're 0.5 and they're 1, and this one is located at the basically 1 meter mark, and this one is at the 3 meter mark. Therefore, our center of mass for the system, x center of mass, would look like 0.5 kilograms times 1 meter, so 1.0 meter, plus 1.0 kilograms times 3.0 meters divided by 0.5 kilograms plus 1.0 kilograms. So this is 0.5, 3.5, so we have 3.5 divided by 1.5. And if you do the math, you end up getting about 2.33 repeating meters. And so now here's where our center of mass is. If we kind of bring it up here, this is 2, 2.1, 2.2, 2.3, 2.4. This is roughly at my 2.33 meters mark, as best as I'm going to get with this resolution. Okay, so you've seen the calculation now of a center of mass. Now what I really want to do with this is actually kind of run the simulation and pay attention to what these two masses do, but also pay attention to what the center of mass does. So we'll hit start, they collide. Notice that the center of mass didn't move at all during this. So initially it was like the system is balanced, our center of mass never moved, it didn't move before, it didn't move after. Now, is that always the case? Well, we can mess around with things like the elasticity. So I'm resetting this, we're still at same mass values, all that. Can change the elasticity. If it's 0% elastic, that means that they should collide and stick together, which probably means they're going to be stopped right here. So let's see. They've stopped here, or they've stopped with this at the center of mass for the system. Okay, and if I reset it, I can change the elasticity to something else. They collide, bounce. Okay, this thing still hasn't moved. Now, is it true to say that the center of mass will not move at all, ever? No. Let me change, for example, this value to, let's say to 2. So we'll just make the mass number 1 the larger mass now. So that's going to move where the center of mass is. You can go about calculating where that should be and comparing to where it is. But if I play, you'll notice that the center of mass now actually moves. The other thing that you may notice, let's repeat that, let's slow it down. You'll notice that before and after the collision, here's before, here's after, the center of mass motion actually retains the same velocity before and after, and that's true whether we make it a perfectly elastic collision like this. That's true if we make it a perfectly inelastic collision, like this. Hello? My mouse pad is being a little dumb. Here's a perfectly inelastic collision. Bing! And it's still moving at the same velocity as it was before. If we go to like full speed, you can also see it. Bing. And if you want to slow down the recording and go back and watch this yourself, you can kind of try or open up the simulation yourself for that matter. You can get how fast the center of mass velocity is by basically figuring out how far has it traveled per how much time before and after the collision. I'm not going to do all that in today's video because it'll run too long. And whoops, now we have a problem, which is that I changed something and I'm telling it to reset and it's not happy with me. So now I have to reload the whole site. That is great, but there are some technical glitches on occasion. Alright, so let's put our center of mass back on here. Let's repeat. Now I've got the masses set at 1.5 and 0.5, and so now the center of mass is moving in the opposite direction. So you should notice that in each of these collisions, no matter what has happened, as long as there's not some external force on the system, I basically don't have any change in the center of mass. Does that happen in 2 dimensions as well, you may be wondering? So let's look. Here's going to be a 2-dimensional, and I'm first going to take off the reflecting border. I've got the center of mass. We'll do a little bing. Okay, so let's see what the center of mass is doing. So did it retain the same motion the whole way? Let's move this more like this and this more like this, and let's see what happens. Bing. Okay. Did this thing retain the same motion the whole time? Yes. And here, let's let them drift off, and then we'll return them. Let's go back to no elasticity, or as close to it as it'll let me go. Bing. Again, center of mass motion did not change in this interaction. Okay, now you may wonder, why is it that I took away the reflecting border? Well, the reflecting border is actually a sort of outside force for this system. So if I include a reflecting border, bing, as soon as I reflect off the border, an external force has been applied on the system, and so now the center of mass actually gets to change. So that's an external force being applied to the system. If you apply an external force to the system, you get a change to the center of mass velocity. Okay, let's reset them. Let's knock off the reflecting border, but let's add another ball to the system. Okay, so another ball to the system basically means that we can have a multiple body collision. And let's see what happens with the center of mass when I do this. Zoop. Bing. No change. Okay. Let's make this a little bit more aggressive so that we get a true 3-ball collision. Zoop. Bing, bing. No change. Okay, so as long as it's only a collision between the objects and you have no external forces on the system, your center of mass motion doesn't change. Center of mass retains the same velocity. So we may want to ask, what would the center of mass velocity be given by? Well, as it turns out, it's basically found in very much the same way as you find regular velocity. It's just, instead of doing it for one object or for another, you pick the center of mass of the system and ask, what is its displacement per time? So V center of mass is basically delta x center of mass over delta t. Same way as you would have found a velocity if I just said I have a ball and it's rolled this far in this much time. Okay, and this does not change, or doesn't change, unless there is an external force. So this statement that the center of mass doesn't change unless there is an external to the system force acting on one or more objects in the system, this is actually equivalent or akin to or implied by and implies conservation of linear momentum. A statement which I will not in this short video prove, but which you could prove by working through the math if you'd like. And that is all that I'm going to do in this short video. Thanks for watching. I hope you learned something from it, and I do plan to have a follow-up video in which I give some kinds of examples of this. So until then, thanks for watching.